In the previous two examples where we computed a probability, the number of total outcomes was fairly easy to picture, fairly simple to picture, because we knew there were only 6 sides to the die, so there were 6 possible outcomes. You could roll a 1, you could roll a 2, on up through 6. Let's consider the following probability. We want to compute the probability of rolling a sum of 7 when rolling a fair die twice, or when rolling 2 fair dice at the same time. This one's got a little bit more depth to the problem, so let's go ahead and tackle it. First, let's talk about the total number of possible outcomes. We can see that this top row is considering when the first die is a 1, and then it goes through the options for what the second die could be. So when the first die is a 1, the second die could be a 1. When the first die is a 1, the second die can be a 2, it can be a 3, a 4, a 5, or a 6. So it rolls through all of those possible options. Going down the column, the first column, this is when we consider the second die as a 1, and it rolls through the changes of the first die. We can see from this table, we could count the possible total outcomes here for rolling 2 dice, but we can see that it's 6 rows and 6 columns. So that's 6 times 6. There are 36 total possible sums of the die. There are 36 total possible outcomes. The first roll is a 1, the second roll is a 1. The first roll is a 1, the second roll is a 2, etc. Each of these is considered a unique outcome. So the probability of the dice being a sum of a 7 is the number of ways to get a 7 divided by the total number of outcomes. And here, the total number of outcomes is the 6 outcomes on the first die times the 6 outcomes on the second die, which ends up being 36. Now let's look at the number of ways to get a sum of a 7. Notice that if you roll a 6 on the first die and a 1 on the second, they add to a 7. A 5 on the first die and a 2 on the second is a 7, a 4 and then a 3 and then a 4, a 2 and then a 5, or a 1 and then a 6. If you look, each of these diagonals are the numbers that are possible sums of the dice. This diagonal is a 2. These 2 add to a 3. These 3 add to 4. These 4 add to 5, 6. The middle diagonal is 7, 8, 9, 10, 11, and 12. So making a picture sometimes will really help us out. So we can see that all the possible ways to get a sum of a 7, there are 6 of them. We've circled them on this picture. So there's 6 ways to roll a 7 divided by our 36 total possible outcomes. So the probability of a sum of a 7 when rolling 2 fair dice is 1/6. How many possible outcomes are there when you're rolling 3 dice? A picture would be much harder to draw. It would be humongous. It turns out this little trick that we found here, where the number of possible outcomes is the number of outcomes on the first die times the number of outcomes on the second die, works out for any number of dice. So the total number of possible outcomes is 6 times 6 times 6, just like we did in the previous example, and that ends up being 216. And that's because there's 6 outcomes on the first die, 6 on the second, and 6 on the third. The law of large numbers is one of the laws that we want you to definitely know by the end of this semester. It comes up in this chapter, and it comes up in a couple chapters from now as well. So let's go ahead and introduce it. If a random phenomenon with numerical outcomes is repeated many times independently, the mean of the observed outcomes, that is the sample mean, approaches the expected value. The expected value is another name for population mean. In a large number of independent repetitions of a random phenomenon, such as coin tossing, averages, or proportions, which really are averages, are likely to become more stable as the number of trials increases. The law of large numbers is a statement about means and proportions, not about sums and counts. The following is a picture of the law of large numbers in action. So notice how we read this picture. On the first toss, we can see that the proportion of heads is 1. So that means that 100% of the flips at that point were heads. So that means that the first flip must have been heads. We can see that this number goes down. This proportion goes down. So by about the fourth flip, it looks like we've gotten some tails, because the proportion of heads goes down. And in fact, it goes down under a half, this dotted line. So that means by the fourth and fifth flip, well, by the fourth anyways, we had less than half heads. So that means we had more tails than heads. And this seems like a plausible outcome. If we were to flip a coin 4 times, we could get 1 heads and 3 tails. That happens quite often. So as we flip, we get to our 5th flip, it looks like our 5th or 6th, it looks like we go above a half, we go back down, up and down, up and down, up and down. And as we get to 50 tosses, it looks like the proportion of heads is stabilizing. It's more straight. It's not so jagged up and down. As we get to 100, it's stabilizing and it's getting close to the true probability, the true proportion, which should be a half. And 500 and 1,000, it's really stabilizing, meaning the proportion of heads out of 1,000 flips, since that's a large number, 1,000 is a large number, the proportion that we see in our sample of 1,000 should be close to the population value, and we know the true probability is a half. So this picture is of the law of large numbers in action. Question. Suppose you toss a fair coin 9 times and get tails all 9 times. What are the chances you'll get another tails on the 10th flip? Well, when we're playing games and we get excited, sometimes we think emotionally and not rationally. Lots of people would say the chances are pretty low that you're going to get another tails because it seems unlikely to get that many tails in a row. But these are independent. Coin flips are independent. And what do we mean by that? We mean that they have no memories. Just because you got 9 tails previously, that coin still has just a 50% chance on any given flip. So the chances you'll get another tails on the 10th flip is still 50%. The law of large numbers says that sample mean gets close to the population mean, or the expected value, as you get a really large number of trials. But in the short term, there's no guarantee that everything's going to even out and you'll get half and half. So we still want to think rationally when we think about probability. A probability that none of us like to think about is when we're discussing risky outcomes, risky behaviors. So risk. Do we think about risk differently than the experts? Let's think for just a minute about cancer clusters. If you hear of a large number of people in a town that come down with cancer, it can cause panic and fear. When we suspect a cluster in our neighborhood, we tend to be upset and not think statistically. Let's think about this for a second. Cancer accounts for more than 23% of all deaths in the United States. So there are approximately 558,040 people that will die of cancer this year. That's a fairly high percentage, so there are bound to be clusters of cancer cases just by chance. This is well studied. We have seen sometimes that the public does not think statistically. Let's explore this a little bit further. We have 2 types of probability. One looks at the personal judgment of how likely, and the other looks at what happens in many repetitions. So the personal judgment of how likely is the personal probability that we talked about at the beginning of chapter 17. The other one looks at what happens in many repetitions. This is empirical probability. And theoretical probability is what would happen in many repetitions too if we could observe the outcome many, many times. Experts tend to look at what happens in many repetitions, and the public looks to personal judgment. So what's considered risky? Approximately 115 people die in an automobile accident every day in the United States. That's about one person every 13 minutes, yet we all get into cars on a regular basis. Approximately 1,440 college students will die this year due to alcohol-related accidents, yet there are plenty of college students attending parties with alcohol on any given night. If 1,440 college students will die this year due to alcohol-related accidents, this is about 4 deaths per day. Why are there still plenty of parties on any given night where college students are drinking? According to the U.S. Department of Education, roughly 20 million students are enrolled in college. Now, I rounded that a lot, but we're just going to use a nice round number. What is the probability of a college student dying in an alcohol-related accident this year? Well, there are 1,440 approximately that die each year, divided by approximately the 20 million who are enrolled in school, and that comes out to be 7.2 times 10 to the negative fifth, which is 4 zeros in front of the 7.2, the 7.2. So a really tiny, tiny, tiny chance. So does this help you understand why there's such a difference between what the experts consider risky and what we consider risky? It's really hard to comprehend a probability that small. So there are 3 things we'll discuss when we're thinking about the differences between what we consider risky and what the experts consider risky. Number 2 on the list is the one we just illustrated. It's hard to comprehend really small probabilities. Number 1, think about fear of riding on an airplane. A lot of people are afraid to ride on airplanes, but not afraid to get in cars, even though you're much more likely to be unsafe in a car. So why are we afraid to ride in airplanes? Some of us are afraid because it seems like we don't have any control. We're not flying the plane. We can't do anything if the engines fail. There's nothing we can do. So we feel safer when a risk seems under our control than when we can't control it. And the third one, the probabilities for some risks are estimated by experts from complicated statistical models. So they have more information than we would have.